Hello everyone, welcome to Tech with Shaping Pixel. Today in this video, we are going to cover Microsoft Azure Data Fundamentals DP-900 Study Cram. If you haven't subscribed to our channel, please subscribe to Tech with Shaping Pixel. Let's start our video. Cloud Computing. Cloud computing is the provision of computing services, including servers, storage, databases, networking, software, analytics, and intelligence over the internet to provide rapid innovation, flexible resources, and economies of scale. Cloud computing is an on demand delivery of services over the internet. IT services which are managed by cloud are infrastructure, networking, databases, and storage. You typically pay only for the cloud services you use, helping to lower your operating costs, run your infrastructure more efficiently, and scale with your business needs. Need for cloud computing. Create, test, and build cloud native applications. Analyze, store backup, and recover data. Drive in intelligence. Stream audio video anytime, anywhere, and on any device. Benefits of cloud computing. Cost optimization and speed, scalability, reliability, productivity, and flexibility, increased performance, and data security. Azure. What is Azure? Azure Cloud Computing refers to computing services which are offered and managed by Microsoft over the internet. Azure Cloud Platform is a collection of more than 200 products and cloud services designed to help you deliver new solutions to solve today's challenges and create tomorrow's. Build, deploy, and manage applications across multiple clouds, on premises, and at the edge with the tools and frameworks of your choice. Different types of cloud services. Cloud computing service models. Infrastructure as a service, platform as a service, software as a service, serverless. Cloud computing service models. Infrastructure as a service. Infrastructure as a service gives you complete control over your cloud resources. In an infrastructure as a service model, hardware, network connectivity, and physical security are maintained by the cloud provider. Use case. Infrastructure as a service is the ideal environment for managing and running testing and development cycles because of its powerful computing and networking capabilities. Platform as a service. In platform as a service, the cloud provider looks after the physical infrastructure, physical security, and internet connection in a platform as a service environment. In addition, they look after the middleware, operating systems, development tools, and business intelligence services that go into a cloud solution. Use case. Platform as a service enables developers to use pre-built software components to create applications. Software as a service. The most comprehensive cloud service model in terms of products is software as a service. Renting or using a fully functional application is what software as a service basically entails. Use case. Software as a service allows users to use business productivity applications and use cloud based email, and messaging applications. Different types of cloud services. Serverless. In cloud computing, serverless architecture refers to a method that lets developers create and run apps without having to worry about maintaining the underlying server infrastructure. It doesn't mean that there aren't any servers. Rather, developers can concentrate entirely on writing code because the cloud provider looks after the servers. Serverless computing enables developers to build applications faster by eliminating the need to manage infrastructure. With serverless applications, the cloud service provider automatically provides, scales, and manages the infrastructure needed to run the code. Use case. Event driven scenarios, microservices, and applications with varying workloads. Microsoft Azure core data concepts. Data is present in many forms, such as in structures and formats, and has shown an exponential increase by the various systems, applications, and devices. In today's world, it's easier and cheaper for businesses to gather and store data. They use software to collect and analyze this information, helping them make important decisions and increase profits. Having good data skills is essential for any organization to succeed. Microsoft Azure core data concepts, common data formats, storage options, common data workloads, rules and responsibilities, Microsoft Azure Data Services. Common data formats. Data comes in various formats like structured, semi structured, and unstructured. Structured data adheres to a specific schema or model, making it easy to manage and predict. Semi structured data has some structure but allows flexibility. Unstructured data does not have a predefined schema. Types of data formats. Data is basically information like numbers or descriptions that we use to keep track of things. It's organized in structures that represent important parts of a business like customers, products, or sales orders. Each part usually has specific details like a customer's name, address, or phone number. Data can be classified into three types: structured, semi structured, and unstructured. Structured data. Structured data follows a set pattern or structure, meaning all the data has consistent fields or characteristics. Typically, this structured data is organized in tables where each row represents an individual piece of information and each column represents a specific detail or attribute. Features of structured data. Structured data conforms to a specific data model and has a well defined structure. It follows a consistent sequence and can be easily accessed and used by both humans and computer programs. Structured data is typically stored in tabular formats such as databases and spreadsheets. Each data element corresponds to a specific field or column in the schema, and each record or row represents a specific instance of that data. For example, in a customer database, each record might have fields for the customer's name, address, phone number, or email address. Semi-structured data. Semi-structured data refers to the information that doesn't have a rigid structure like traditional databases but still exhibits some level of organization. Unlike structured data with fixed schemas, semi-structured data allows for variability in the structure between different instances. Example of semi-structured data is JSON, a format used to organize such information. Features of semi-structured data. Well-defined schema or data model. Table format. Clearly known symptoms. Easy access and querying. Unstructured data. Unstructured data refers to information that lacks a predefined data model or organization. Unlike structured data, which fits neatly into tables or databases with fixed schemas, unstructured data doesn't have a specific format or structure. It includes things like text documents, emails, social media posts, images, videos, and audio files. Features of unstructured data. Unstructured data does not conform to a specific data model or have an easily identifiable structure. It does not have a predefined format and does not fit well with rows and columns like structured data in databases. Examples of unstructured data include web pages, images, videos, memos, and reports. File storage. Storing data in files is essential for any computer system. Files can be kept on local hard drives or USB drives, but in many organizations, they are stored centrally in shared systems. Nowadays, the centralized storage often happens in the cloud, offering cost effective, secure, and dependable storage for vast amounts of data. The choice of file format for storing data depends on ample factors such as the nature of the data, the requirements of applications and services that interact with the data, whether the data files need to be human readable or are optimized for efficient storage and processing. Storage options. Data can be stored in different ways. Files. Storing data in files is common. Databases. Structured data is often stored in relational databases like SQL Server, MySQL, and PostgreSQL. Delimited text files. Data is often stored in plain text format with specific separators between fields and rows. The most widely used format is called comma-separated values, in which rows conclude with a carriage return or new line and fields are separated by commas. Tab-separated values and space-delimited formats, in which fields are separated by tabs or spaces, are two other popular formats. JavaScript object notation. JSON is a widely used format for structuring data in a human-readable way. It's commonly used for transmitting data between a web server and a web application, as well as for storing configuration data. Extensible markup language. XML is a way to organize and move data. It uses tags to label pieces of information, forming a hierarchy like a tree. XML is great for sharing data between systems because it's easy for both people and computers to understand. Binary large object. In simpler terms, all files are actually stored as ones and zeros. But in human readable formats, these binary digits are converted into printable characters using encoding schemes like ASCII or Unicode. Optimized file formats. While human readable file formats for structured and semi structured data are handy, they are not always the most efficient for storage and processing. Specialized formats like Avro, ORC, and Parquet have been developed to optimize these tasks. Avro stores data in rows with a JSON header, making it good for compression and minimizing storage needs. ORC organizes data into columns for faster read and write operations, commonly used with data warehouse systems like Apache Hive. Parquet is also columnar, organizing data into row groups for efficient processing and supporting nested data types with effective compression. What is a database? A database serves as a centralized system for storing and accessing data through queries. While the file system can be seen as a basic form of database, in professional data contexts, a database typically refers to a dedicated system designed specifically for managing data records, offering enhanced functionality beyond simple file storage. Types of databases. Relational databases. Relational databases are widely utilized for storing and retrieving structured data. Information is gathered into tables, each representing a specific entity like customers or products. Every entity instance is given a primary key for unique identification, which is then used to link related data across different tables. For example, in a relational database, a customer's primary key can be linked to a sales order record, showing which customer made the purchase. This referencing of keys helps maintain data normalization by reducing redundant information. For instance, storing a customer's details only once rather than duplicating them for every order. Tables are handled and queried using structured query language. Non-relational databases. Non-relational databases, also known as NoSQL databases, diverge from traditional relational databases by not adhering to a strict relational schema. While many NoSQL databases support SQL-like languages, they offer flexibility in data modeling and storage structures, making them suitable for handling diverse data types and scale horizontally. They are basically of four types and they are as follows. Key value databases store records as pairs of unique keys and associated values, accommodating data in any format. This structure provides simplicity and flexibility in managing and retrieving data, making key value databases suitable for various applications and use cases. Document databases are a specialized type of key value database where each value is a JSON document optimized for efficient parsing and querying. This design enables flexible data modeling and querying, making document databases well suited for handling complex and evolving data structures in modern applications. Column family databases organize tabular data into rows and columns, similar to traditional databases, but with the added flexibility of dividing columns into groups called column families. Graph databases store entities as nodes interconnected by links, representing relationships between them. This structure enables efficient storage and traversal of complex relationships, making graph databases ideal for applications requiring rich and interconnected data models such as social networks, recommendation systems, and network analysis. Common data workloads: transactional versus analytical. Transactional data processing focuses on real time operations such as updating records or processing transactions. Analytical data processing involves querying and analyzing large datasets for insights. Azure offers services such as Azure SQL Database for transactions and Azure Synapse Analytics for analytics. Transactional data processing. Transactional data processing systems are the backbone of business computing, focusing on recording specific events that organizations need to track. These transactions can range from financial activities like fund transfers in banking to retail operations such as processing customer payments. Each transaction represents a discrete unit of work. OLTP, Online Transactional Processing. Transactional systems, also known as online transactional processing systems, manage large volumes of transactions, often handling millions in a day. These systems prioritize rapid access to data, ensuring efficient processing of business operations. OLTP relies on databases optimized for efficient read and write operations to handle transactional workloads, including CRUD operations. These operations are executed transactionally to maintain data integrity. OLTP systems enforce ACID semantics to ensure reliable and secure transaction processing. ACID properties. Atomicity. Transactions are viewed as cohesive units, either executing entirely or not at all. If any part of a transaction fails, the entire transaction is rolled back, ensuring data consistency and integrity. Consistency. Concurrent transactions operate independently without impacting each other, ensuring that the database remains in a consistent state despite simultaneous operations. Isolation. Simultaneous transactions run independently, ensuring they don't disrupt each other and always lead to a stable and coherent database state. Durability. Once a transaction is committed, its changes are permanent and resilient. Analytical data processing. Analytical data processing involves systems optimized for reading large volumes of historical data or business metrics. These systems are typically read only or read mostly, focusing on analyzing data rather than making frequent updates. Analytics can be performed on snapshots of data at specific points in time or on a series of snapshots to identify trends and patterns over time. The architecture of an analytical processing system can vary, but for enterprise scale analytics, a common structure often includes the following components. Operational data undergoes an extract, transform, load process, funneling into a data lake for analysis. In a Spark-based data lakehouse or a relational data warehouse, data is organized into tables. This data may then be aggregated and transformed into an online analytical processing model, computing aggregated measures across various dimensions. Data stored across the data lake, data warehouse, and analytical models is accessible for querying to generate reports, visualizations, and dashboards. Data lakes. They are referred to extensive large analytical processing scenarios where a large amount of data with respect to files can be collected and analyzed. Data warehouse. Data warehouses serve as a proven method of data in a relational schema optimized for read operations, primarily supporting and data visualizing queries. Data lakehouse. Data lakehouse represent a newer approach, merging the scalable storage capabilities of a data lake with the relational querying features of a data warehouse. While maintaining the flexibility and scalability of a data lake, they introduce relational querying semantics. To enhance query performance, the table schema may necessitate some denormalization, which involves duplicating data from OLTP sources. OLAP models offer aggregated data storage tailored for analytical tasks, facilitating drill up or down capabilities across dimensions. For instance, users can analyze total sales by region, city, or individual address. As OLAP data is pre-aggregated, queries to retrieve summaries are executed swiftly. In data analytics, an OLAP model facilitates aggregated data storage optimized for analytical tasks. Users at different stages. Data scientists explore and model data in the data lake. Data analysts query the data warehouse for complex reports. Business users access pre-aggregated data via reports or dashboards for decision making. Data workloads, roles and responsibilities. A diverse range of roles exists in data management, blending business, engineering, and research functions. While organizational definitions may vary, common roles include business analysts, data scientists, data engineers, and hybrid roles, each with distinct tasks and responsibilities. Data analysts analyze data, create reports, and gain insights. Data engineers design and build data pipelines, ETL processes, and data warehouses. Database administrators manage databases, ensure performance, and maintain security. Developers work with data APIs, build applications, and integrate data services. Solution architects design end-to-end data solutions using Azure services. Following roles that deal with the data in the organizations. Database administrator. A database administrator oversees the design, implementation, and maintenance of database systems both on-premises and in the cloud. They ensure databases operate smoothly, optimize performance, and collaborate with stakeholders to establish backup and recovery protocols. Additionally, they manage data security, granting appropriate access privileges to users while safeguarding sensitive information. Data engineer. A data engineer collaborates with stakeholders to design and deploy data workflows encompassing tasks like data ingestion, cleansing, and storage for analytics. They leverage diverse data platform technologies from databases to file stores to manage data effectively, ensuring data privacy across cloud and on-premises environments. They oversee pipeline management and monitoring for optimal performance. Data analyst. A data analyst empowers businesses to leverage their data assets effectively. They analyze data to uncover patterns, create analytical models, and facilitate advanced analytics through reports and visualizations. By translating raw data into actionable insights aligned with business needs, they enable informed decision making. Microsoft Azure Data Services. Microsoft Azure serves as a robust cloud platform, driving applications and IT infrastructure for global enterprises. Offering a wide array of services, it caters to diverse cloud needs, encompassing both transactional and analytical data workloads. Azure offers a variety of services for data professionals. Azure SQL Database, a managed relational database service. Azure Cosmos DB, a globally distributed NoSQL database. Azure Data Lake Storage, scalable storage for big data and analytics. Azure Databricks, a collaborative analytics platform. Azure Synapse Analytics, an integrated analytics service for big data and data warehousing. Azure Stream Analytics, real-time data processing. Azure Machine Learning, for building and running ML models. Below are some frequently utilized Azure Cloud services for data. Azure SQL DB. Azure SQL encompasses a range of relational database solutions built on the Microsoft SQL Server engine. Azure SQL includes various relational database solutions like Azure SQL Database, Azure SQL Managed Instance, and Azure SQL VM. Database administrators set up and manage these systems for business applications. Data engineers use Azure SQL databases to extract, transform, and load transactional data into analytical systems. Data analysts query Azure SQL databases for reports, while in larger organizations, data is combined with other sources for enterprise analytics. Azure Database for open source relational databases. Azure offers managed services for popular open source relational database systems. Azure Database for MySQL, user-friendly database commonly used in LAMP stack apps. Azure Database for MariaDB, performance-optimized DB system compatible with Oracle DB. Azure Database for PostgreSQL, a hybrid relational object database supporting both relational and custom data types. Database administrators manage these systems for transactional applications, while data engineers and analysts use them as data sources for analytical solutions and reports. Azure Cosmos DB. Azure Cosmos DB is a large-scale NoSQL database system that supports various APIs, allowing storage of data in different formats like JSON documents, key value pairs, column families, and graphs. In organizations, database administrators or software developers may handle provisioning and management of Cosmos DB instances. Data engineers integrate Cosmos DB data into analytical solutions, enabling modeling and reporting by data analysts. Azure Storage. Azure Storage is an essential Azure service allowing you to store data in different ways. Blob containers store binary files efficiently and at a low cost. File shares share files over a network similar to those in corporate networks. Tables store data quickly in key value pairs, ideal for applications needing fast data access. Data engineers use Azure Storage to host data lakes, which organize files and folders for easy management in a distributed file system. Azure Stream Analytics. Azure Stream Analytics is a tool on Azure that processes data streams in real time. It takes data from a source, applies a query to extract and modify it, and then sends the results to another place for analysis or more work. Data engineers use Azure Stream Analytics to fit into data analytics systems that collect streaming data for use in analytics or to show data in real time. Azure Data Explorer. Azure Data Explorer is a fully managed, high performance big data analytics platform that makes it easy to analyze high volumes of data in near real time. The Azure Data Explorer toolbox gives you an end to end solution for data ingestion, query, visualization, and management. With Azure Data Explorer, you can ingest terabytes of data in minutes in batch or streaming mode. You can query petabytes of data with results returned within milliseconds to seconds. Azure Data Explorer provides high velocity, low latency, and linear scale ingestion of raw data. Microsoft Purview. Microsoft Purview helps big companies manage their data better. It creates a map of all the data a company has and tracks where it comes from and where it goes. This helps find reliable data for analysis and reports. Data engineers use Microsoft Purview to make sure data is managed well across the company. This makes sure the data used for analysis is accurate and reliable. Microsoft Azure Relational Data Considerations. Relational data. Introduction to relational data. In a relational database, data is organized into tables, each representing a different entity like customers or products. Rows and tables store specific information about each entity, while columns define the categories of data. Tables ensure structured data organization, with columns allowing flexibility for optimal information. Relational data. The main characteristics of a relational database are: all data is tabular. Entities are modeled as tables. Each instance of an entity is a row in the table, and each property is defined as a column. All rows in the same table have the same set of columns. A table can contain any number of rows. A primary key uniquely identifies each row in a table. No two rows can share the same primary key. A foreign key references rows in another related table. For each value in the foreign key column, there should be a row with the same value in the corresponding primary key column in the other table. Normalization. Normalization is the process of organizing data in a database efficiently. It involves breaking down a database into smaller, manageable parts and structuring those parts to reduce redundancy and dependency. This helps ensure data integrity and makes the database easier to maintain and use. Why normalization is used? Suppose we have a database for a school. In this database, we want to keep track of students and the subjects they are enrolled in. Initially, we might create a single table called student info with the following columns. Each row in this table represents a student, and the columns hold information about each student's ID, name, address, and the subjects they are enrolled in. However, this approach has some problems. Redundancy. If a student takes more than 3 subjects, we would need to add more columns to accommodate them. This can lead to wasted space and make the table harder to manage. Dependency. The information about subjects is mixed with information about students. If we need to update the details of a subject, we would have to update multiple rows in the table, leading to potential inconsistencies. To address these issues, we can normalize the database. We can create separate tables for students and subjects and establish a relationship between them using foreign keys. First, we create a students table with columns for student ID, name, and address. Each row in this table represents a unique student. Second, we create a subjects table with columns for subject ID and subject name. Each row in this table represents a unique subject. Finally, we create a third table called enrollments with columns for student ID and subject ID. This table serves as a bridge between the students and subjects tables, indicating which students are enrolled in which subjects. This normalized structure eliminates redundancy by storing each piece of data once and establishes a clear relationship between students and subjects. It also makes the database more flexible and easier to maintain. Structured Query Language. SQL is short for Structured Query Language. It's a tool used to talk to relational databases. You use it to ask questions or make changes to the information stored in a database. Almost all big databases understand SQL. It's like a common language that helps computer understand what you want to do with the data. Common SQL statements. Some examples of DBMS which use SQL are Microsoft SQL Server, MySQL, PostgreSQL, MariaDB, and Oracle. You can use SQL to do almost everything you need with a database, like getting data, adding new data, changing existing data, or even creating and deleting entire databases. While there are standard SQL performs CRUD operations, different database systems often have their own extra features. These extras help with things like security and customizing how the database works. Different dialects of SQL include Transact SQL, used in Microsoft SQL Server and Azure SQL services. PGSQL, implemented in PostgreSQL. PL or SQL, used in Oracle databases, standing for Procedural Language or SQL. There are three types of SQL statements. Data definition language. You use DTL statements to create, change, or delete tables and other database objects like stored procedures and views. Some common DTL statements are create. Make a new object in the database like a table or a view. Alter. Change the structure of the object like adding a new column to a table. Drop. Get rid of objects from the database. Rename. Change the name of object that already exists. The drop statement is strong because it deletes things permanently. If you drop a table, all its data disappears forever unless you have a backup copy. Data control language. Database administrators use DCL statements to handle who can access what in a database. They grant, deny, or revoke permissions for specific users or groups. The three main DCL statements are grant, give permission for certain actions. Deny, refuse permission for certain actions. Revoke, take back previously granted permissions. Data manipulation language. DML statements are used to work with the rows and tables. You can insert new rows, edit existing rows, and retrieve data using these statements. If you decide you no longer need a row, you can also delete it. DML statements are as follows. Select, get rows from a table. Insert, add new rows to a table. Update, change data in existing rows. Delete, remove existing rows from a table. Database objects. Apart from tables, a relational database can include other components to enhance data management, streamline tasks, and boost performance, and those components are as follows. View. A view in a database is a virtual representation of data derived from the results of a select query. For example, creating a view named Employee Info that displays selected columns from an employee's table. Stored procedure. Stored procedure is a pre-compiled set of SQL statements that are stored in a database and assigned a name. This allows SQL query to be easily executed and reused multiple times without the need for rewriting and recompiling it each time. An example of a stored procedure in SQL might be a procedure named getEmployeeDetails that retrieves information about employees from a database. Index. Index is used to look for the data in the table. Creating an index involves sorting and storing column data with pointers to table rows. When querying by the indexed column, the database uses it to quickly retrieve data, avoiding the need to scan the entire table. Index command in SQL is used to create the index of the table and creates a tree-based structure to find the data in no time. Index. Azure SQL services and capabilities. SQL Server on Azure Virtual Machines. An Azure Virtual Machine running SQL Server offers infrastructure as a service, virtualizing hardware infrastructure for compute, storage, and networking. This makes it ideal for migrating existing on-premises SQL Server installations to the cloud via lift and shift. Azure SQL Managed Instance. A platform as a service offering providing high compatibility with on-premises SQL Server instances, abstracting hardware and OS. It includes automated updates, backups, and maintenance, minimizing administrative tasks for database server management. Azure SQL Database. A highly scalable, fully managed platform as a service database service designed for cloud environments, offering core capabilities of on-premises SQL Server. Ideal for new cloud-based applications. Azure SQL Edge. SQL engine tailored for IoT applications, handling streaming time series data. SQL Server on virtual machines. SQL Server on Azure virtual machines offer full SQL Server functionality in the cloud, eliminating the need to manage on-premises hardware. This approach supports lift and shift migrations with minimal changes, making it suitable for applications requiring access to specific operating system features. SQL Server on virtual machines. SQL Server on a virtual machine allows for full control and flexibility in developing and testing SQL Server applications. It's an optimal choice when organizations already possess IT resources for managing virtual machines. This approach facilitates rapid development and testing without the need for on-premises hardware. Supports lift and shift migrations with minimal changes. Offers scalability by easily adjusting resources like memory, CPU, and disk space. Business benefits. Cost efficiency. SQL Server on virtual machines eliminates the need for on-premises hardware, reducing capital expenditures associated with purchasing and maintaining physical servers. Rapid deployment. Virtual machines enable quick deployment of SQL Server instances, facilitating faster time to market for applications and services. Disaster recovery and high availability. Virtual machines support disaster recovery and high availability configurations, ensuring business continuity and data protection. Compatibility. SQL Server on virtual machines provides compatibility with existing applications and tools, facilitating seamless migration and integration with existing infrastructure. Azure SQL Database Managed Instance. Azure SQL Managed Instance offers a fully controllable SQL Server instance in the cloud, allowing for multiple databases on the same instance. It automates backups, software patching, and monitoring while providing complete control over security and resource allocation. Dependencies on Azure services include Azure Storage for backups, Azure Event Hubs for telemetry, and Azure Key Vault for transparent data encryption, ensuring secure and reliable operation. All communications are encrypted and signed using certificates with constant verification for trustworthiness through certificate revocation lists to protect data integrity. Business benefits. Simplified management. Automated backups, software patching, and monitoring reduce administrative overhead, allowing IT teams to focus on strategic initiatives rather than routine maintenance tasks. Scalability allows for easy scaling of resources to accommodate changing workload demands, ensuring optimal performance and availability without over-provisioning. Flexibility supports multiple databases on the same instance, providing flexibility in application architecture and database consolidation. Azure SQL Database. Azure SQL Database is a highly scalable, fully managed platform as a service database service designed for cloud environments, offering core capabilities of on-premises SQL Server. Ideal for new cloud-based applications. Two forms of Azure SQL Database are as follows. Single database. This option allows for quick setup and management of a single SQL Server database in the cloud. Microsoft handles server management while users configure databases and manage data. Resources can be pre-allocated or specified in a serverless configuration. Automatic scaling ensures optimal resource allocation and privacy is maintained by Microsoft. Elastic Pool. This option, known as Elastic Pool, allows multiple databases to share resources like memory, storage, and processing power, reducing costs and optimizing resource utilization. Users create a pool for their databases, ensuring dedicated access to shared resources. Elastic Pool is beneficial for managing databases with fluctuating resource demands. Business benefits. Cost efficiency. Pay as you go pricing model and options for resource optimization, reducing overall costs associated with database management. Security. Enterprise grade security features such as data encryption, threat detection, and access controls help protect sensitive data and ensure compliance with industry regulations. Rapid development. Integration with Azure services and development tools facilitates rapid application development and deployment, accelerating time to market. Azure Database Services for open source database systems. MySQL. MySQL, an open source relational database management system, stands out for its cost effectiveness, robust features, and widespread adoption. Its open source nature fosters a collaborative community, driving innovation and customization. MySQL comes in three editions: Community, Standard, and Enterprise. The Community Edition, popular for web applications on Linux and Windows, is free. Standard Edition offers improved performance with a different data storage technology. Enterprise Edition provides advanced tools like enhanced security and scalability. Azure Database for MySQL. Azure Database for MySQL is a platform as a service offering in Azure based on MySQL Community Edition. It includes high availability and scalability with pay as you go pricing. Automatic backups and point in time restore are included. Connection security and configurable server parameters are provided. It offers a global database system without managing hardware or administration tasks, though some security and administrative functions are managed by Azure. Benefits of Azure Database for MySQL are as follows: built-in high availability, increased performance, scalability on demand, robust security, automated backups and point-in-time restore, flexible pricing model, and comprehensive monitoring and alerting. MariaDB. MariaDB, developed by the original creators of MySQL, is a modern database management system optimized for enhanced performance. It offers compatibility with Oracle database and stands out for its built-in support for temporal data. This feature allows tables to retain multiple versions of data, enabling applications to query historical data effectively. PostgreSQL. PostgreSQL is a versatile hybrid relational object database system that combines the structure of relational tables with the flexibility of custom data types. It supports storing and manipulating geometric data like lines and polygons. PostgreSQL is extensible, allowing the addition of core modules that can be executed by queries. It uses its query language called PGSQL, a variant of SQL, enabling the creation of stored procedures within the database. Azure Database for MariaDB. Azure Database for MariaDB is a managed service in Azure built on MariaDB Community Edition. Azure handles all management tasks requiring minimal administration after provisioning and data transfer. Benefits of Azure Database for MariaDB are as follows: free built-in high availability, predictable performance with pay-as-you-go pricing, instant scalability, secure data protection, automatic backups and point-in-time restore for 35 days, enterprise-level security and compliance. Azure Database for PostgreSQL. Azure Database for PostgreSQL is a platform as a service offering designed to run PostgreSQL in the Azure cloud. It delivers comparable benefits to the MySQL service, including availability, performance, scaling, security, and administrative ease. Azure Database for PostgreSQL Flexible Server. The Flexible Server Deployment option for PostgreSQL is a fully managed database service in Azure. It offers extensive control over server configurations and customization options while also providing features for cost optimization. Benefits are as follows. Ensures high availability with built-in failure detection and failover mechanisms. Users can leverage familiar tools like pgadmin to manage and monitor databases. Microsoft Azure non-relational data considerations. Azure Blob Storage. Azure Blob Storage is Microsoft's cloud storage service that allows you to store large amounts of unstructured data, such as text or binary data, in the cloud. In Azure storage accounts, blobs are stored in containers, which group related blobs together. Access control for reading and writing blobs is managed at the container level. Within containers, blobs can be organized in a virtual folder hierarchy. However, these folders are virtual and don't support folder-level access control or bulk operations. Types of blob storage are block blobs. A block blob is comprised of blocks, each up to 4000 MIB. It can hold up to 190.7 TIB with a maximum size exceeding 5000 MIB. Blocks are the smallest units for read or write operations. Block blobs are ideal for storing large, binary objects that can change rarely. Page blobs. A page blob consists of fixed size 512-byte pages and supports random read or write operations at the page level. It can store up to 8 TB of data and is commonly used for virtual disk storage and Azure virtual machines. Append blobs. An append blob is a type of block blob designed for append operations, allowing only adding blocks to the end. Each block can be up to 4 MB and the maximum size of an append blob is over 195 GB. Access tiers in blob storage are hot tier. It's an online tier optimized for storing frequently accessed or modified data. The hot tier has the highest storage costs but the lowest access costs. Cool tier. It's an online tier optimized for storing rarely accessed or modified data. Data on cool tier should be stored for at least 30 days. A cool tier has lower storage costs and higher access costs compared to a hot tier. Cold tier. It's an online tier optimized for storing data that is rarely accessed or modified, but still requires fast retrieval. Data in cold tier should be stored for at least 90 days. A cold tier has lower storage costs and higher access costs compared to a cold tier. Archive tier. It's an offline tier optimized for storing data that is accessed infrequently and has flexible latency requirements on the order of hours. Data in the archive tier should be stored for at least 180 days. Azure Data Lake Storage Gen 2. Azure Data Lake Store and Azure Data Lake Storage Gen 2 are services for storing hierarchical data in analytical data lakes used by big data solutions. Gen 2 is integrated into Azure Storage, offering scalability of blob storage, cost control of storage tiers, and compatibility with major analytical systems while retaining hierarchical file system capabilities. Services such as Hadoop in Azure HD Insight, Azure Databricks, and Azure Synapse Analytics can utilize Azure Data Lake Store Gen 2 as a distributed file system to process large data volumes. Azure File Storage. Azure Files provide fully managed file shares in the cloud, accessible via the industry standard Server Message Block Protocol, Network File System Protocol, and the Azure Files REST API. Azure Files provide cloud-based network shares similar to on-premises file shares, facilitating access to files for multiple users and applications. Azure file shares can be mounted simultaneously through cloud or on-premises deployments. By leveraging Azure Files, organizations can eliminate hardware costs and maintenance overhead while enjoying high availability and scalable cloud storage for files. Azure files are created within a storage account and allow sharing up to 100 TB of data. This data can be distributed across multiple file shares. Each file can be up to 1 TB in size, with quotas available to limit share size. Azure File Storage supports up to 2000 concurrent connections per shared file. Once a storage account is created, files can be uploaded to Azure File Storage via the Azure portal or tools like Easy Copy. Azure File Sync service can be used to synchronize local copies of shared files with data in Azure File Storage. Azure File Storage has two performance tiers: Standard, utilizing hard disk-based hardware, and Premium, using solid-state disks for higher throughput at a higher cost. Network sharing protocols. Server message block. SMB file sharing is widely used across various operating systems, including Windows, Linux, and Mac OS. Network file system. NFS shares are utilized by certain Linux and Mac OS versions. Creating an NFS share requires a premium tier storage account and configuring a virtual network for access control. Azure Table Storage. Azure Table Storage is a NoSQL database service where data is organized into tables, with each table containing key value pairs. Each pair is represented by a row, which contains columns for storing data fields. Azure Table Storage is highly scalable, offers high availability, and is suitable for storing semi-structured data such as key value pairs or entities with properties. Each row in an Azure table must have a unique key consisting of a partition key and a row key. Azure Table Storage lacks features such as foreign keys, relationships, stored procedures, and views. Data is denormalized, with each row typically containing all the data for a logical entity. In contrast to relational databases, Azure Table Storage doesn't split information across multiple rows and tables. It's commonly used for applications requiring fast access to large volumes of data, such as web applications, IoT devices, and login systems. Azure Table Storage enhances access speed by partitioning tables. Partitioning groups rows based on a common property or partition key, ensuring rows with the same key are stored together. Partitioning not only organizes data but also enhances scalability and performance in the following manners. Partitions operate independently, capable of dynamically adjusting in size as rows are added to or removed from them. There is no limit to the number of partitions a table can accommodate. Including the partition key in search criteria reduces the data volume examined, enhancing performance by minimizing I/O operations needed to locate the data. Azure Cosmos DB. Azure Cosmos DB is a globally distributed multi-model database service offered by Microsoft Azure. It's designed to provide high availability, low latency, and scalability for building modern, globally distributed applications. Azure Cosmos DB supports multiple APIs, allowing developers to work with data using familiar programming semantics. The internal data structure is abstracted, enabling seamless storage and querying of data using various APIs. Cosmos DB leverages indexes and partitioning for fast read and write performance, scaling seamlessly to handle massive data volumes. It's designed to provide high availability, low latency, and scalability for building modern, globally distributed applications. Scenarios to use Cosmos DB. Cosmos DB is a highly scalable database service in Azure, managing partition space automatically and maintaining indexes without administrative overhead. It's utilized by major Microsoft products like Skype and Xbox for global scale applications. Ideal for scenarios needing high scalability and global availability. Scenarios are as follows. Cosmos DB is ideal for IoT and telematics applications handling large data ingestions effectively. It seamlessly integrates with analytics services like Azure Machine Learning, Azure HD Insight, and Power BI for data analysis. Real-time data processing is also possible using Azure functions triggered by incoming data. In retail and marketing, Cosmos DB is employed by Microsoft for its e-commerce platforms within the Windows Store and Xbox Live. It's a go-to choice in the retail sector for catalog data storage and event sourcing in order processing pipelines. In the gaming industry, the database tier plays a vital role in delivering personalized content, such as in-game stats and leaderboards via the cloud. Games require low latencies for responsive gameplay and must handle sudden surges and request rates during launches and updates. A fast and scalable database solution like Cosmos DB is essential for ensuring an immersive gaming experience. Azure Cosmos DB is frequently integrated into web and mobile applications, offering robust capabilities for modeling social interactions, third-party service integration, and creating personalized experiences. Its SDKs empower developers to craft feature-rich iOS and Android apps using the widely adopted Xamarin framework. Azure Cosmos DB for Table. Azure Cosmos DB for Table is a high-performance, scalable solution tailored for key-value table data akin to Azure Table Storage but with superior scalability and performance capabilities. You can utilize the Table API with language-specific SDKs to access your service endpoint and fetch data from the table. Azure Cosmos DB APIs. Azure Cosmos DB is a fully managed, serverless distributed database by Microsoft, supporting relational and non-relational workloads. Developers can quickly build or migrate applications using preferred open source engines like PostgreSQL, MongoDB, and Apache Cassandra, selected upon instance, provisioning based on data type and developer expertise. Azure Cosmos DB for NoSQL. Microsoft's native non-relational service designed for the document data model is called Azure Cosmos DB for NoSQL. It offers a smooth experience by handling data in JSON document format with efficiency and using SQL syntax for data manipulation in a novel way. Azure Cosmos DB for Apache Cassandra. Azure Cosmos DB for Apache Cassandra is compatible with the widely used Apache Cassandra, an open source database employing a column family storage structure. While column families resemble tables in a relational database, they offer flexibility by not requiring every row to have same columns. Azure Cosmos DB for MongoDB. Azure Cosmos DB for MongoDB allows developers to utilize MongoDB client libraries and code seamlessly within Azure Cosmos DB. MongoDB, a widely used open source database, stores data in binary JSON format. Its query language employs a compact, object-oriented syntax, simplifying data manipulation through method calls. Azure Cosmos DB for PostgreSQL. Azure Cosmos DB for PostgreSQL is a globally distributed, native PostgreSQL database that scales effortlessly to meet your app's demands. It automatically shards data for high scalability. You can begin building apps on a single node server group, just like with PostgreSQL elsewhere, and seamlessly scale to multiple nodes as needed. PostgreSQL, a relational database management system, allows you to define relational tables of data. Azure Cosmos DB for Apache Gremlin. Azure Cosmos DB for Apache Gremlin is designed for working with graph structured data, where entities are represented as vertices, forming nodes in a connected graph. These nodes are linked by edges, representing relationships between them. Analytics workload on Microsoft Azure. Data warehousing architecture. Large-scale data analytics architecture typically consists of several core components, although the specific technologies employed may vary. The key elements typically include are data ingestion and processing. Data from various sources, including transactional data stores, files, and real-time streams, is loaded into either a data lake or a relational data warehouse. This loading process typically involves extract, transform, and load, or extract, load, and transform operations where data is cleaned, filtered, and restructured for analysis. In ETL, transformation occurs before loading, whereas in ELT, data is first loaded and then transformed. Regardless of the approach, the resulting data structure is optimized for analytical queries. Data processing is carried out by distributed systems capable of parallel processing using multi-node clusters to handle high data volumes effectively. Includes batch processing for static data and real-time processing for streaming data. Data ingestion pipelines. A data ingestion pipeline in Azure is a series of automated processes and workflows designed to collect, process, and load data from various sources into Azure data storage services. These pipelines play a critical role in modern data architectures, enabling organizations to ingest large volumes of data from diverse sources efficiently and reliably. In Azure, large scale data ingestion is effectively managed through orchestrated ETL processes facilitated by pipelines. Azure Data Factory serves as a robust tool for creating and executing these pipelines, while Azure Synapse Analytics or Microsoft Fabric offer similar capabilities within a unified workspace for comprehensive data analytics management. Pipelines in Azure consist of activities that operate on data, with input datasets providing source data and activities defining data flows to incrementally manipulate the data until an output dataset is generated. These pipelines seamlessly connect to external data sources, enabling integration with a diverse range of data services. Analytical Data Store. An analytical data store serves as a repository for structured data optimized for analytical queries and reporting. It typically stores historical data aggregated from various sources, including transactional databases, files, and real time streams. Large scale analytics data stores encompass relational data warehouses, file system based data lakes, and hybrid architectures blending features of both, often referred to as data lakehouses or lake databases. Analytical data model. While data analysts and data scientists can directly access data in the analytical data store, it's typical to create one or more pre aggregated data models for producing reports, dashboards, and interactive visualizations. These models, often referred to as cubes, aggregate numeric data values across dimensions. They encapsulate relationships between data values and dimensional entities to facilitate drill up or drill down analysis. Data warehouse and data lake storages. Data warehouse. A data warehouse is a relational database optimized for data analytics, not transactional workloads. Data from transactional stores is transformed into a schema suited for analytics. Numeric values are stored in central fact tables related to dimension tables representing entities for aggregation. Example: sales order data in a fact table can be aggregated by customer, product, store, and time dimensions. This schema is known as a star schema, often extended into a snowflake schema by adding tables for dimensional hierarchies. Example: product related to product categories. These ideal for structured schemas and SQL based querying of transactional data. Data warehouse and data lake storages. Azure Synapse Analytics. Azure Synapse Analytics is a comprehensive solution tailored for large scale data analytics, integrating various technologies and capabilities. It's a unified platform as a service, is a complete data analytics solution on Azure, offering various capabilities. Pipelines move and transform data using the same technology as Azure Data Factory. SQL, a powerful database engine for data warehousing. Apache Spark, process large scale data using different programming languages. Azure Synapse Data Explorer, analyze log and telemetry data in real time using custom query language. Data engineers can use Azure Synapse Analytics to create a unified data analytics solution, combining data pipelines, data warehousing, and data lake storage. Data analysts can explore and analyze data using SQL and Spark pools, and integrate with services like Azure Machine Learning and Power BI to gain insights from the data. Features: it merges the reliability of a scalable, high performance SQL server based relational data warehouse with the versatility of a data lake and Apache Spark. Native support for log and telemetry analytics is provided through Azure Synapse Data Explorer pools. Built-in data pipelines facilitate data ingestion and transformation processes seamlessly. All Azure Synapse Analytics services are accessible and managed through a unified user interface known as Azure Synapse Studio. Azure Synapse Studio allows users to create interactive notebooks combining Spark code and Markdown content. Synapse Analytics offers a unified analytics solution within the Azure ecosystem, ideal for organizations seeking a cohesive approach to data analytics. Azure Databricks. Azure Databricks is a cloud based implementation of the Databricks platform renowned for its comprehensive data analytics capabilities. Built on Apache Spark, Databricks offers native SQL functionalities and specialized Spark clusters optimized for data analytics and data science workloads. It features an interactive user interface for system management and data exploration via interactive notebooks. Azure Databricks is a strategic choice for organizations leveraging existing expertise with the platform or operating in a multi cloud environment. Its compatibility across multiple cloud platforms makes it an attractive option for those seeking a cloud portable analytical solution. Azure Databricks is like a special version of Databricks that works seamlessly with Azure. It combines Apache Spark, SQL databases, and a management interface for big data analytics. Data engineers can use Azure Databricks to build analytical data stores using their existing skills with Databricks and Spark. Data analysts can query and visualize data using the easy to use notebook feature in Azure Databricks, all within a web based interface. Big data analytics and AI with optimized Apache Spark. Microsoft Fabric. Microsoft Fabric is an all in one analytics solution for enterprises that covers everything from data movement to data science, real time analytics, and business intelligence. It provides comprehensive services including data lake, data engineering, and data integration in one place. Microsoft Fabric is a complete analytics platform that handles bringing in and organizing data, analyzing data in a unified system, supporting data science and machine learning, real time analytics, visualizing data, and managing data securely. Microsoft Fabric simplifies scalable analytics by offering a unified software as a service solution. Instead of juggling multiple services and interfaces, Fabric provides a single easy to understand product for setting up, managing, and accessing data. Fabric Spun Lake architecture serves as a centralized environment akin to OneDrive for data, where all data is stored in a single open format. OneLake consolidates storage locations across different regions and clouds into a unified logic lake, eliminating the need for data movement or duplication. Data stored in OneLake can be structured or unstructured, and analytical engines in Fabric write tabular data in Delta format for seamless interoperability across different engines. Azure HD Insight. Azure HD Insight is an Azure service supporting multiple open source data analytics cluster types. While not as user friendly as Azure Synapse Analytics or Azure Databricks, it offers versatility for analytics solutions relying on multiple open source frameworks. It is particularly suitable for migrating existing on premises Hadoop based solutions to the cloud. Azure HD Insight is a service on Azure that offers clusters for popular Apache open source big data processing tools such as Apache Spark, a system for processing large amounts of data supporting multiple programming languages like Java, Scala, Python, and SQL. Apache Hadoop, a distributed system using MapReduce to process big data across many cluster nodes. It can also use Apache Hive, which lets you write queries in SQL. Apache HBase, a system for storing and querying large-scale NoSQL data. Apache Kafka, a tool for handling data streams. Data engineers use Azure HD Insight to handle big data analytics tasks that rely on these open source technologies. Azure Data Factory. Azure Data Factory is a service on Azure that helps you create and schedule data pipelines for moving and changing data. You can connect these pipelines with other Azure services to bring data from cloud stores, process it with cloud based tools, and save the results in another store. Data engineers use Azure Data Factory to build ETL solutions which move data from transactional systems to analytical stores in the organizations. Batch processing versus stream processing. Batch processing. Batch processing involves collecting and storing newly arriving data elements, which are then processed together as a batch. The timing of batch processing can be scheduled based on predetermined time intervals, triggered by a certain amount of accumulated data or in response to specific events. Stream processing. Stream processing involves immediate processing of each new piece of data upon arrival, without waiting for the next batch processing interval. Unlike batch processing, which processes data in batches at predefined intervals, stream processing handles data as individual units in real time. Stream data processing is advantageous in scenarios characterized by continuous generation of new and dynamic data. Batch processing versus stream processing. Batch processing involves collecting and storing multiple data records before processing them together in a single operation. Stream processing involves continuously monitoring and handling data in real time as new events happen. Batch processing is suited for processing large volumes of data collected over time, often in bulk quantities. Stream processing is designed to handle continuous streams of data, regardless of volume, with the ability to process data incrementally as it arrives. Batch processing it generally has higher latency as data is processed in predefined intervals, which may lead to delays in obtaining insights or results. Stream processing offers lower latency as data is processed in near real time, enabling quick insights and responses to emerging trends or events. Batch processing is commonly used for historical analysis, periodic reporting, and offline data processing where real time insights are not critical. Stream processing is ideal for scenarios requiring real time monitoring, alerting, anomaly detection, and immediate responses to events such as fraud detection, IoT telemetry analysis, and clickstream analysis. Batch processing typically requires resources to be provisioned and allocated for processing batches of data at specific intervals. Stream processing requires continuous resource allocation to process data as it arrives, often utilizing scalable and distributed computing resources to handle fluctuating data volumes and processing demands. Advantages of batch processing: efficient handling of large data volumes. Batch processing allows for the processing of large volumes of data in a structured manner. Scheduled execution. Tasks can be scheduled to run at times when computer systems are typically idle, such as overnight or during off peak hours, maximizing resource utilization. Predictable processing. Processing occurs at predefined intervals, providing predictability and facilitating resource planning and management. Disadvantages of batch processing: time delay. There's a delay between data ingestion and result availability due to the processing occurring at predetermined intervals. Data readiness requirement. All input data for a batch job must be prepared before processing can commence. This necessitates thorough data verification and validation. Interruption vulnerability. Problems such as data errors or program crashes during batch jobs can halt the entire process. Even minor data inconsistencies can prevent the batch job from executing properly. Combine batch and stream processing. Many large-scale analytics solutions blend both batch and stream processing methods to facilitate historical and real-time data analysis. Stream processing solutions typically capture real-time data, perform filtering or aggregation, and present insights through real-time dashboards and visualizations. This diagram illustrates the integration of batch and stream processing within a large-scale data analytics architecture. Streaming data events are captured in real time. Data from other sources is ingested into a data store, often a data lake, for batch processing. If real-time analytics is not required, captured streaming data is returned to the data store for subsequent batch processing. Stream processing technology is used to prepare streaming data for real-time analysis or visualization, often by filtering or aggregating data over temporal windows. Non-streaming data is periodically batch processed to prepare it for analysis, with results persisted in an analytical data store, often referred to as a data warehouse, for historical analysis. Results of stream processing may also be persisted in the analytical data store to support historical analysis. Analytical and visualization tools are employed to present and explore both real-time and historical data. Common elements of stream processing architecture. General architecture for stream processing. Events like sensor signals or social media posts produce data. This could be a log file entry, a sensor emission, or any digital occurrence. Data is collected in a streaming source for processing. This could be a cloud folder, a database table, or a queue ensuring ordered and unique event processing. Event data undergoes processing using perpetual queries. These queries select, project, or aggregate data values based on event types or time periods, such as counting sensor emissions per minute. Processed stream data is sent to an output like a file, database table, real-time dashboard, or another queue for further processing. Azure Real-Time Analytics. Azure offers various technologies for real-time analytics of streaming data. Azure Stream Analytics, a platform as a service solution for defining streaming jobs, ingesting data from streaming sources, applying perpetual queries, and writing results to an output. Spark Structured Streaming, an open source library for building intricate streaming solutions on Apache Spark services like Azure Synapse Analytics, Azure Databricks, and Azure HD Insight. Azure Data Explorer, high performance service for ingesting and analyzing time series data either in batch or real time. Works as a standalone service or integrated with Azure Synapse Analytics. Sources for stream processing. Azure Event Hubs ensures reliable event processing for various data sources. Azure IoT Hub, specifically designed for efficiently handling data from IoT devices. Azure Data Lake Storage Gen 2, highly scalable storage suitable for both batch and streaming data. Apache Kafka, open source solution offering flexible event streaming. Azure Stream Analytics. Azure Stream Analytics is a service that helps analyze data as it streams in. Here's what it does. Ingest data. It brings in data from various sources like Azure Event Hubs, IoT Hubs, or storage containers. Process data. It runs queries on the data to pick out, organize, and summarize the information. Output results. The processed data is then sent to different destinations like Azure Data Lake, SQL Database, Synapse Analytics, Functions, Event Hubs, Power BI, and more. Apache Spark on Microsoft Azure. Apache Spark is a robust free tool that lets you spread your tasks across multiple computers to get things done faster. It makes it easy to work with big sets of data and ensures that even if something goes wrong with one of the computers, your work keeps running smoothly. When deployed on Microsoft Azure, Apache Spark enables users to process large-scale data sets efficiently in a distributed computing environment. Spark Structured Streaming. Spark Structured Streaming is a library used for processing streaming data in Apache Spark. It's based on data frames, which are like tables of data. With this library, you can read data from sources like Kafka or files and continuously update a data frame with new data from the stream. Spark Structured Streaming. Then you can run queries on the data frame to select, project, or aggregate the data, often in time-based windows. The results of these queries create another data frame that can be saved for analysis or more processing. Real-time analytics in Microsoft Fabric. Real-time analytics in Microsoft Fabric involves continuously analyzing data as it arrives, allowing for immediate insights and responses. Its one-lake architecture combines storage across different regions and clouds into a single logical lake without moving or duplicating data. Fabric supports various data formats, including structured and unstructured data, and optimizes data processing for both batch and streaming scenarios. This enables organizations to analyze data in real time, generate insights, and make informed decisions swiftly. Data visualization in Microsoft Power BI. Data analysts utilize analytical models and directly access analytical stores to generate reports, dashboards, and visualizations. Non-technical users within an organization engage in self-service data analysis and reporting. The resulting visualizations depict trends, comparisons, and key performance indicators for the business or organization. These visual representations may include printed reports, graphs, or charts in documents or presentations, web-based dashboards, and interactive environments, facilitating visual data exploration. Power BI tools and workflow. Data analysts have various tools to visualize data, like Microsoft Excel's charts and built-in widgets and platforms, such as Azure Synapse Analytics. But for big business needs, a comprehensive solution supporting advanced data modeling, interactive reports, and secure sharing is essential. Microsoft Power BI. Microsoft Power BI is a set of tools and services that help data analysts create interactive data visualizations for business users to use. Core concepts of data modeling. Analytical models help organize data for analysis. They are like organized tables where you can see numbers you want to analyze and categories to group them. Tables. In the context of databases, a table is a collection of data organized into rows and columns. Each row represents a single record or data entity, while each column represents a specific attribute or field of the data. Tables provide a structured way to store and manage related information, making it easier to query and manipulate data. Schema. A schema defines the structure of the database, including tables, relationships between tables, constraints, indexes, and other database objects. It serves as a blueprint for organizing and representing data in the database. A schema can include multiple tables, each with its own set of columns and relationships to other tables. Schema also defines data types, constraints, and rules for storing and retrieving data, ensuring data integrity and consistency. Attribute hierarchies. Attribute hierarchies represent the relationships between different attributes or dimensions in a data model. These hierarchies define the logical structure of data, allowing users to navigate and analyze data at various levels of granularity. For example, in a sales database, you might have a time dimension with attributes like year, quarter, month, week, and day. These attributes form a hierarchical relationship where year contains quarters, quarter contain months, months contain weeks, and weeks contain days. Attribute hierarchies allow users to navigate data from higher levels of aggregation to lower levels of detail. Attribute hierarchies facilitate aggregation of data across different levels of granularity. Aggregations can be performed by rolling up data from lower levels to higher levels in the hierarchy or by drilling down to view detailed data. Attribute hierarchies play a crucial role in data analysis and reporting, enabling users to explore data in a structured and intuitive manner. They provide a hierarchical organization of data attributes, making it easier to understand the relationships between different dimensions and analyze data from various perspectives. Analytical modeling in Power BI. With Power BI, you can create a structured model for analyzing your data. You start by importing your data tables from different sources. Then, using Power BI Desktop, you can define your model by connecting tables, creating hierarchies, and adjusting how your data looks and behaves. This helps you organize your data in a way that makes it easy to analyze and understand. Power BI capabilities. Build data driven analytics. Businesses have a lot of data, from customer and employee info to sales figures. But just having data isn't enough. You need to understand it and share its meaning. That's where Power BI comes in. Power BI is a set of tools that helps you make sense of your data. It can take data from different places like Excel or databases and turn it into easy to understand visuals. You can connect to your data, clean it up, make it look nice, and then share it with others. It's all about making data more accessible and understandable for everyone in your business. Different Power BI elements. Capacities. In Power BI, capacities are the resources used to store and deliver your content. There are two types: shared and dedicated. Shared capacities are used by multiple Microsoft customers, while dedicated capacities are exclusively for one customer. You need a subscription for dedicated capacities. By default, workspaces are created on shared capacities. Workspaces. Workspaces in Power BI are like folders where you can organize your dashboards, reports, data sets, and data flows. There are two types: My Workspace and regular workspaces. My Workspace is like your personal folder where only you can access your content. You can share your dashboards and reports from here if needed. Regular workspaces are for collaborating with colleagues. You can add co-workers to these workspaces to work together on dashboards, reports, and data sets. Most workspace members need Power BI Pro licenses except for one special case. Semantic models. In Power BI, a semantic model is a collection of data from various sources. It can include data from Excel, SSAS, Salesforce, and more. These models are linked to workspaces and can be shared among workspace members with certain rules. Shared semantic models. Business intelligence involves creating standardized data models called semantic models, which serve as the single source of truth. Sharing and reusing these models streamlines report creation, ensuring consistent data usage across the organization for better decision making. Simply select Power BI semantic models when building reports to access shared models. Reports. A Power BI report is a collection of visualizations like charts and maps. You can create reports from scratch, import them from shared dashboards, or have Power BI generate them when connecting to datasets. Template apps. Power BI template apps let partners create apps without coding and share them with Power BI customers. Partners create content and publish it for customers to use. Dashboards. A dashboard is like a canvas where you can add tiles and widgets to display visualizations. Each tile shows a single visualization from a report or a Q&A. You can also pin entire report pages to a dashboard as a single tile. Cleaning and transforming data in Power BI Desktop. Combining data from different sources often requires cleaning and transformation before creating reports. Power BI Desktop offers the Power Query Editor to help you prepare your data. Power BI Desktop has three views: report, data, and model for different stages of analysis. Power Query Editor helps shape and transform data for use in reports and visualizations. Transforming data, modifying data structure to suit your needs. Cleaning data, preparing data for optimal visualization and modeling. Power Query Editor offers tools to clean and transform data, including combining rows, aggregating values, and more. AI insights to spot trends and anomalies. Power BI's insights feature automatically finds interesting patterns and trends in your data while you are using reports and dashboards. It alerts you about these insights and explains them without needing any special setup. Power BI uses AI to provide insights in different ways. Insights for reports. It finds patterns and trends in your data while you are using reports. Insights for individual visuals. It explains changes in data points within visuals. Insights for dashboard tiles. It presents data from tiles in interactive visuals. Quick insights for datasets. It automatically generates insights on datasets. AI insights for data models in Power Query. It offers access to pre-trained machine learning models from Azure Cognitive Services. In Power BI, notifications are a key part of insights. While you are working on reports, Power BI checks for insights automatically. When it finds something interesting, you get a notification. You can then decide whether to check out the insights or ignore them. Notifications help you stay on top of important trends like a sudden increase in sales in a certain area. Top insights are the most notable ones, based on factors like how recent or significant they are. Insights. The Insights pane in Power BI shows three types of insights. Anomalies. These are unexpected occurrences like a sudden spike in temperature on a thermostat. Trends. These are patterns found over time, such as sales steadily increasing month by month. Key performance indicator analysis. This helps compare current performance to a set target, like comparing current sales to a sales goal. Anomalies. An anomaly is when something unusual happens in a series of data over time, like a sudden jump or drop. An algorithm calculates a normal range, and anything outside of that range is called an anomaly. There are three types of anomaly insights. Significant anomaly. This is when the anomaly is especially big or important. The anomaly score shows how far away it is from what's expected. Recent anomaly. This is the most recent unusual event in the data. Anomaly summary. This gives a summary of all the anomalies found in the data. When an anomaly is detected, Power BI checks the data to see if there are any patterns or explanations for why it happened. It ranks these explanations by how likely they are. Trends. A trend happens when there's a long lasting increase or decrease in data over time. Power BI's algorithm follows several steps to find these trends, like smoothing out the data and checking for statistical significance. It ignores temporary changes, like sales spikes during holidays. There are four main types of trends: long trend, a significant and lasting trend in the data; sleep trend, a significant trend with a sharp increase or decrease. Recent trend, the most recent significant trend. Trend reversal, a recent change in trend direction compared to the previous pattern. When a trend is detected, Power BI figures out which categories or factors caused the change. It ranks possible explanations based on how much they contributed to the trend. KPI analysis. KPI analysis with a target compares the current value to a set target. If the difference is big compared to other segments, it's considered important. Without a target, it compares the value itself to others. Power BI looks at categories with higher or lower values than expected. For analysis with a target, it ranks possible explanations based on how far the value is from the target. For analysis without a target, it ranks explanations based on how unusual the value is compared to others. Business value of Power BI. Nowadays, we know that data can make businesses better and earn more money. Let's take a look at a real life example. The Miami Heat, a basketball team in the US. They use Power BI a lot and it's made a big difference for them. With Power BI, the Miami Heat increased their season ticket sales by 30% and saved about $1 million. They wanted to understand their fans better, even though there are lots of them. Power BI helps them analyze their data and predict how many people will come to each game. They have been really accurate, getting within 4% of the actual numbers for the whole season. So, using Power BI and other Microsoft tools can help businesses make more money and make better decisions. Features of data models in Power BI. The features of data models in Power BI include relationship management. Power BI allows you to create relationships between different tables in your data model, enabling you to combine data from multiple sources. DAX calculations. Data analysis expressions is a formula language used in Power BI to create custom calculations and measures based on your data. Hierarchies. You can create hierarchies within your data model to organize data into logical levels, making it easier to analyze and visualize. Aggregations. Power BI supports aggregation functions like sum, average, count, etc., allowing you to summarize and analyze data at different levels of granularity. Data import and transformation. Power BI provides tools for importing and transforming data from various sources, ensuring that your data is cleaned and ready for analysis. Modeling view. The modeling view in Power BI desktop allows you to view and manage relationships, calculations, and other aspects of your data model. Row-level security. Power BI enables you to implement row-level security to restrict access to specific rows of data based on user rules or permissions. Interactive reports in Power BI. In Power BI, the visuals in a report that show related data are automatically connected and can be interacted with together. Considerations for Power BI. Power BI offers various ways to show your data visually. It has lots of built-in options and you can add even more. This unit talks about some common visualizations, but there are many more out there. Tables and text. Tables and text are straightforward ways to share data. Tables work well when you have lots of related data to show, while text values in cards are handy for highlighting key numbers or metrics. Bar and column charts. Bar and column charts are useful for comparing numbers across different categories visually. Line charts. Line charts are handy for comparing things like categories and trends, especially over time. Pie charts. Pie charts are commonly used in business reports to show how different categories contribute to a whole. Scatter plots. Scatter plots are handy for comparing two sets of numbers and finding any relationship or connection between them. Maps. Maps are useful too for comparing data across various geographical areas or locations visually.